Electromagnetism is everywhere, shaping our reality in ways we rarely notice. It's as fundamental as gravity, yet often invisible and unfelt. This force powers the light you see, the devices you use, and even the atoms in your body. A compass points north, your phone connects to a network, and a magnet sticks to your fridge, all thanks to electromagnetism. Atoms themselves are held together by this force. Without it, matter wouldn't exist. Electromagnetism is the architect of our reality. This guide will take you on a journey into this unseen world. We'll start with the basics. Electric charge, the source of all electromagnetic phenomena. Then we'll explore electric and magnetic fields. Two sides of the same coin. We'll demystify Maxwell's four famous equations, the foundation of classical electromagnetism. No complex math, just simple words and clear examples. Prepare to see the world in a new light, literally. We'll uncover the physics behind everyday magic, why a balloon sticks to a wall, how a wire lights up a city, why the sky is blue. The answers all lie in electromagnetism. By the end, you'll not only know about this force, but appreciate its elegance and impact on every moment of your life. Let's begin our exploration. Imagine the world without light, electricity, or magnetism. Life as we know it would vanish. Every screen, every signal, every spark is a product of this force. The journey ahead will reveal how deeply electromagnetism is woven into the fabric of existence. From the smallest particles to the largest galaxies, its influence is everywhere. Understanding it isn't just for scientists, it's for anyone curious about how the universe works. So, open your mind to the unseen. Get ready to discover the force that shapes your world. The adventure starts now. Let's dive in. Everything begins with electric charge, a basic property of matter, like mass. Protons are positive, electrons are negative, and neutrons are neutral. The unit of charge is the Coulomb, but even a single electron's charge is tiny. Like charges repel, opposites attract. This simple rule explains countless phenomena. Rub a balloon on your hair, electrons move, creating opposite charges that attract. But how strong is this force? That's where Coulomb's law comes in. It tells us the electric force grows with bigger charges and shrinks rapidly with distance. Double the distance, the force is 4 times weaker, an inverse square law. This force is incredibly powerful, far stronger than gravity at the atomic scale. The electric force between an electron and a proton is about 1,000 trillion times stronger than gravity. That's why electromagnetism, not gravity, holds atoms and molecules together. It's the glue of the microscopic world, creating the matter we see and touch. Without it, there would be no chemistry, no biology, no life. Every spark, every shock, every static cling is a glimpse of this force in action. Coulomb's law is the foundation for understanding electric interactions. It's simple, elegant, and explains why matter holds together. Next, we'll see how charges influence the space around them. Let's move from charges to fields. The story of electromagnetism is just beginning. Stay with us. A single charge creates an invisible region of influence, an electric field. Think of it as a web of force surrounding the charge. Any other charge entering this field feels a push or pull. Electric field lines show the direction and strength of this force, outward for positive, inward for negative. Where lines are close, the field is strong; where they're far apart, it's weak. In thunderstorms, huge electric fields build between clouds and ground, leading to lightning. The field can even store energy, as in a charged capacitor. Electric fields aren't just math, they're real physical entities. They shape the space around every charge, waiting to interact. When you see lightning or feel static, you're witnessing electric fields in action. The concept of the field is central to all of electromagnetism. It's how charges talk to each other across space. Next, we'll see how magnetism fits into this picture. The story continues with magnetism. Let's explore the other half of the force. Now let's talk about magnetism. Magnets always have both a north and south pole. Cut one in half, you get 2 new magnets. Unlike electric charges, magnetic monopoles don't exist in nature. Like poles repel, opposites attract, just like with electric charges. The force you feel pushing magnets apart or snapping them together is magnetism in action. All magnetism comes from moving electric charges. In permanent magnets, it's the motion of electrons inside atoms that creates the effect. In materials like iron, these tiny atomic magnets align, producing a visible magnetic field. Even Earth is a giant magnet thanks to molten iron moving in its core. Magnetism and electricity are deeply connected. Let's see how moving charges create magnetic fields. A moving charge or a magnet creates a magnetic field, symbolized by B. Magnetic field lines loop from north to south outside a magnet, forming closed loops. Unlike electric fields, magnetic fields don't have a beginning or end. Magnetic fields only affect moving charges, deflecting them sideways, a force called the Lorentz force. This sideways push causes charged particles to spiral, as seen in the aurora borealis. The sun's charged particles hit Earth's magnetic field, creating the northern lights. Electric currents, flows of electrons, also create magnetic fields. Hans Christian Ørsted discovered this when a current deflected a compass needle. A current in a wire creates a magnetic field circling the wire. Stronger current, stronger field. This is how electromagnets work. From motors to MRI machines, this principle powers modern technology. Now, let's unlock the laws that govern these fields. Maxwell's equations describe how electric and magnetic fields behave. The first, Gauss's law for electricity, says the electric field flowing out of a closed surface depends on the charge inside. Imagine a bubble around a charge. The number of field lines leaving the bubble matches the charge inside. Make the bubble bigger, the field lines spread out, so the field gets weaker. This explains why electric forces follow an inverse square law. Gauss's law also explains electrical shielding. Inside a closed metal box, the electric field is zero. That's why you're safe in a car during lightning. This law is a powerful tool for understanding and calculating electric fields. Next, the law for magnetism. Gauss's law for magnetism states that magnetic field lines always form closed loops. There are no magnetic monopoles, no isolated north or south poles. For any closed surface, the net magnetic field flowing out is always zero. Unlike electric fields, magnetic fields have no sources or sinks. This law has been tested for decades. No monopoles have ever been found. If one were discovered, it would revolutionize physics. For now, magnetic field lines always loop back on themselves. This is a fundamental difference between electricity and magnetism. The two Gauss's laws capture this elegant symmetry. Now let's see how changing fields create new forces. The story gets dynamic. The last two Maxwell equations reveal the dynamic heart of electromagnetism. Faraday's law, a changing magnetic field creates an electric field. Move a magnet near a wire and you generate electricity. This is how generators work. The faster the change, the bigger the current. This principle powers everything from power plants to bicycle dynamos. The fourth equation, the Ampere-Maxwell law, says a changing electric field creates a magnetic field. Maxwell's insight completed the symmetry. Changing electric fields and magnetic fields create each other. This feedback loop lets fields travel through space as waves. These self-sustaining waves are electromagnetic waves. Light, radio, X-rays, all are born from this dance of changing fields. Maxwell's genius was seeing this unity. The equations don't just describe forces, they predict waves that move at the speed of light. This was a turning point in science. Let's see how this discovery changed the world. The symphony of electromagnetism is everywhere. Maxwell's equations predicted waves of electric and magnetic fields traveling at the speed of light. He realized, light itself is an electromagnetic wave. This unified electricity, magnetism, and optics. The electromagnetic spectrum includes radio microwaves, infrared visible light, ultraviolet X-rays, and gamma rays. All are the same phenomenon, differing only in wavelength and frequency. This understanding powers our world: lights, phones, the internet, medical imaging, and more. Every screen, every signal, every broadcast is a triumph of electromagnetism. The digital revolution is built on these laws. From magnets on fridges to fiber optic cables, electromagnetism animates modern life. Maxwell's equations didn't just explain nature, they gave us the tools to shape the future. The study of electromagnetism reveals the hidden unity of the universe. As technology advances, our mastery of this force will unlock new possibilities. The journey into electromagnetism never truly ends. Its influence is everywhere, shaping the world and the future.